Hello and welcome to today's lecture. So, I would begin by doing a brief recap of what we had discussed in last class, mainly ways of quantifying dispersion in a population or a sample, right. And one of the widely used metrics for characterizing this variation in the data is using standard deviation, right. You either use sigma to describe standard deviation of a population, and this is given by summation of x minus mu whole square by capital N, or S is for the sample, which is summation of x minus x bar whole square by n minus 1, right. So, again once again note this minus 1. So, when you are doing a sample, then it is it is thought of that by dividing by n minus 1 you get a better estimate of standard deviation of the population, right. So, what exactly is the practical significance of the standard deviation, and this we had discussed in last class, and which is what Chebyshev's theorem tells us. So, it says that given a number k greater than 1 and a set of n measurements, what you are guaranteed is at least 1 minus 1 by k square proportion of the measurements will lie within k standard deviations of their mean, right. So, if I substitute k equal to 2, then that would become 1 minus 1/4, which is 75% of the measurements are expected to lie within one standard deviation of the mean, which means 75% of the data will lie between mu or x bar minus sigma and x bar plus sigma. So, as an example, you have n equal to 26, mean is 75, variance is 100. So, in this case, if I have x bar is equal to 75 and n is equal to 26, variance is equal to 100. So, I can roughly calculate S is approximately equal to 10, right. So, within 75 plus minus 10, you have 3/4 of the population, right. So, 3/4 of the number of variables will actually lie within this range, which is minus 65 to 85. Similarly, I can do the same thing for 2 standard deviations, and so you have 75 plus minus 20 in this case will have contain 1 minus 1 by 9, that is 8 by 9 fraction of the population. 8 by 9 is roughly 90% of the population. But as I had stated last week in last class, that for a generic distribution, so Chebyshev's theorem is actually a very conservative estimate. So, this is your x bar minus S, x bar plus S, right. So, they say that this much, so this is roughly what we calculated is 75%, and in the generic case, okay, x bar plus 2S and x bar minus 2S, this is 90% of the population. But Chebyshev's theorem is a very conservative in approach. So, it does not make any assumptions of how the distribution of data is there. In contrast, for what you observe for a mound like distribution, or which is Gaussian distribution, a normal distribution, you will see that there is 68% of the data which are expected to be there within plus minus 1 standard deviation. So, as opposed to 75% predicted by Chebyshev's theorem, in normal distribution 68% stay within the plus minus 1 standard deviation, okay. But plus minus 2 standard deviations, 95% of the data is there, okay, and 3 standard deviations, 99.7% of the data are there. So, this also brings us to the concept of Z score, or it is relative standing, right. So, what exactly is Z score? It is basically defined by x minus mean by standard deviation, and you can do this calculation if for a for a particular experiment, if your mean is 25, standard deviation is 4 and x is 30, then Z score returns you a value of 30 minus 25 by 4, which is 1.25. Okay. Now, you can use Z score to get an estimate of whether a particular data point is an outlier or not, and this can be clearly gleaned from this particular example we worked out in last class. So, what you see, if you look at the data points, all the points are clustered between 1 and 4, except for this one particular value, which is 15, right. So, we can clearly see, it seems to us that 15 is outlier or very close to being an outlier. You can do this calculation, we had worked out what exactly its value is, I do not remember, but you can find out whether as per this, this statement if the z score comes out to be greater than 3 or not. Another way of characterizing our relative standing is using the concept of percentile, right. So, pth percentile is the value which is greater than p% of the measurements. So, 100 percentile is essentially, so that person who is in the 100% or 99 percentile is pretty much better than, has performed better than 99% of the population in a class. Okay. So, you can use these particular positions to determine how you will calculate the first quartile or third quartile. The second quartile is of course at position 0.5 star n plus 1 is nothing but the median. Okay. So, this represents at what 25% of the data point is first quartile, 75% of the data point is third quartile, and interquartile range is defined as Q3 minus Q1. Okay. So, using this these values, one can plot what is called a box plot, and in a box plot, so the lowest value is your minimum. Okay. The box outlines, so you have the Q1 which is the first quartile, Q2 or the median, Q3 or the third quartile, and this is your maximum. So, what you also see are points which may lie outside this definition of box. So, if you take this point, this coincides with the maximum value of the distribution, but this point, or for that matter this point, really is much outside the box limits. So, these points are examples of outliers, and it is perhaps not completely surprising that in many experimental data you do have outliers. Okay. So, this square inside the box actually denotes the mean. What you see here in this particular population, you have variables. If you look at the y axis, you have variables which vary all the way from around 20 or 30 or 50 all the way to 600. So, when you take an average, the effect of that 600 is going to have a much greater effect than a value of 50, which is why in this particular case the mean is slightly shifted above the position of the median. So, you take this particular example, it is the other way around, where the median is here and the mean is here. Okay. So, based on this, if you were to plot it in terms of histograms, so as opposed to having a distribution like this where your position of mean, median, mode all coincide, you might either shift to the left or to the right. Okay. So, the way to detect outliers is using this particular formula. So, you can construct fence where the lower fence is given by Q1 minus 1.5 times interquartile range, and the upper fence is Q3 plus 1.5 interquartile range. Okay. So, let us just work out a sample case of how we will actually plot our box plot. Okay. So, let me write down the points. You have the points 350, 300, 520, 340, 320, 290, 260 and 330. Okay. So, first step of course is to sort in ascending order. So, my lowest value here is 260, then 290, I can have 300, I have 320, 320, 330, 2 340s and 1 520. Okay. So, we can already see clearly here that as opposed to all of these points which kind of are clustered together, this data point seems to be out of the plot. Okay. So, but let us find out, do our necessary calculations once again. So, I have 260, 290, 300, 320, 330, 340, 340, 520. So, my total number of measurements is 1, 2, 3, 4, 5, 6, 7, 8. N is equal to 8. That means, okay. So, my median position is going to be somewhere like this. My median value will be half of 320 and 330, okay, equal to 325. the position of Q1 position will be 1 times n plus 1 equal to 9 by 4, it is 2.25. So, after 2, so this is going to be the position of Q1, this is your median, okay, and Q3 position is going to be 3/4 into 9 is 27 by 4 is 6 4 24 6.75. So 1 3 4 5 6 7, right. So Q3 is going to somewhere here, okay. So my Q1 value will be 290 plus 0.25 times 10, which is going to be 290 plus 2.5, 292.5. Q3 is going to be 6.75, 1 2 3 4 5 6 is 340 plus 0.75 into 340. So it will still get the value. So Q3 is in this particular position, 0.75 times 340. No, but the 340 minus 340, which is nothing but 340 only. Okay. So we have calculated the values of Q1 and Q3. So now we need to see our median. So for this particular distribution, I have Q1 as 292.5, Q3 is equal to 340. So which would mean that IQR is equal to Q3 minus Q1 is 47.5. Okay. So now we know that the lower fence, so lower fence Q1 minus 1.5 times IQR, Q1 is 292.5 minus 1.5 into 47.5. So which will be around, let us say 1 times is 47.5, which will be around 250. I do not know the exact value, please calculate that. But as you can see, if you look at our points once more, the lowest value is 260. That means that there are no lower outliers. So this implies that there are no lower outliers. Okay. I can similarly calculate the value of Q3 plus 1.5. So upper fence Q3 plus 1.5 times IQR, Q3 is 340 plus 1.5 into 47.5. So which will give me a value. So if I assume this as 50, so this is approximately is to 340 plus 1.5 times 50. So approximately is 340 plus 50 75 is roughly 415. So this implies that the number, so there is an outlier, there is an upper outlier, and which is nothing, which is the value is equal to 520. Okay. So if I were to construct the plot, my plot would look something like this. Okay. So as you can see that there is no, so the minimum is 260, and because, so this is your lower fence, your upper fence is somewhere here, okay, and this value lies much above. So this means that, so you have an error bar which sticks out, but this is much outside. Okay. So there are actually no points here, there are no data points in this region, okay, because after 340, so where are the points? So because after 340 there is, you directly have 520. Okay. So this just means that there is no data point here, but your error bar, this shows you up to the maximum time there are no points here. Okay. So with that I show you how to generate a box plot. Now we come to another interesting concept of moments. Okay. So as per, so Pearson was the first statistician to make use of moments to describe data. Now how is a moment defined? So you have moment about, so moment about any variable about 0 is defined as summation y to the power r by n, where r can have 1, 2, 3 any value. Okay. So clearly, so this is moment, so this is moment about 0. Okay. So in general moment, so this is the rth moment, this is the rth moment. In general, moment about A is defined by mr star would be in the generic case y minus A whole to the power r by n. Okay. So now let us see what the moments convey. So you have moment about 0, mr star is defined by summation y r by n. It is obvious that if I put r equal to 1, then m1 star is equal to summation y by n, which is nothing, is equal to y bar, right. So first moment about 0 is your mean. What about r is equal to 2? So r equal to 2, then I have m2 star about 0 is summation y square by n, right. So as you can clearly see that this gives me, I know that the way standard deviation or variance is defined, you have a term of y minus y bar whole square by n. So in other words, if you were to go through the moment, so the rth sample moment about the mean would then have this particular value, which is mr is equal to summation y minus y bar whole to the power r by n. Okay. So m2 about 0 is y square. So this would mean that if I main mr about 0, I put y bar is equal to 0, I have y to the power r. So mr about the mean, so in that case mr is defined as summation y minus y bar whole to the power r by n. So m1 in this case will be summation y minus y bar by n, and this is nothing but summation y minus summation y bar by n. So summation y is equal to n times y bar, and summation y bar n times is nothing but n y bar. So this would give me a value of 0. Okay. So first moment about the mean is 0. This obviously brings us to the second case, that what is the second moment about 0. So this would be defined by y minus y bar whole square by n. So as you can see that if this was for a population, m2 is nothing but variance. Okay. So m2 is variance. So I am going to make that approximation, because if it is for a sample, then you have to be n minus 1, but this is very simply is equal to the variance. Okay. So m2 is, I can say population variance. Okay. So similarly, I can calculate this value, which is m3 is equal to summation y minus y bar whole cubed to the power n, right. Now let us consider a very symmetric distribution. If my distribution was symmetric, so there is symmetry, right, in this distribution. If I look at how m3 is defined, then I know that for, if there is a symmetric, would mean that for every value which is to the left of this, there is similar value at similar frequency to the right of this, right. So let us say this is y bar, this is y1 and this is y2. So the frequency of y1 and the frequency of y2 is symmetric, is equal, and that is how the distribution is called, it is a symmetric distribution. In that case, so if I have for every y1, so I have two things, symmetric, and let us say this distance is the same. So y1 minus y bar is equal to, let us say, minus delta y, and y2 plus y bar is going to be plus delta y, y2 minus y bar is going to be plus delta y. So if I do this summation, it just means that for every y1 which is to the left of y bar, So, and whatever contribution this gives, which will be negative in nature, the another point which is equidistant on the positive axis and has same frequency will give me a positive response. And anything cubed, if you have a negative number, its cube is negative, if you have a positive number, its cube is positive. So, if you add these two terms, so it will be like, let us say, f times minus del y cubed plus f times del y cubed, and these two terms equate to 0. So, this would mean that M3, okay, so this would mean that M3 will return you a value of 0 for odd, for symmetric distributions. Okay. And this is same for any MR. So, MR about the mean is going to be 0 for symmetric distributions for R is equal to odd. So, in other words, M1, M3, M1 is 0, M3 is 0, M5 is 0, and so on and so forth. Okay. So, clearly for all symmetric distributions you have the odd moments about the mean return you a value of 0. Okay. Now, let us say the variable y that we are measuring is actually some quantity, it is not just a number, it is a quantity, let us say temperature or height. So, M3 will have, so each of them have different units, right. So, if I were to say y represents height, then unit of M1, okay, in terms of meter, let us say it is in meters, M3 unit is meter cubed, M5 unit is meter fifth. So, in other words, these units are not the same. Can there be a way of compressing this information and coming up with a non-dimensional parameter? And that is what this measure of skewness gives us. Okay. So, skewness is defined in a slightly different way, is A3 is equal to summation of y minus y bar whole cubed by summation of y minus y bar whole square whole to the power of 3 by 2. I can again rewrite as M3 by M2 whole to the power 3 by 2. Okay. So, as what you can clearly see that M3 will have units of meter cubed, M2 will have units of meter square whole to the power 3 by 2 will give you units of meter cubed, and this is after all a number, a dimensionless number. So, this parameter A3 is called a skewness. A3 is called skewness, and for any distribution, so as it is obvious from the word skew itself. So, for any symmetric distribution, my skewness A3 has to be 0. Okay. So, it is neither skewed in this direction or skewed in this direction. Okay. So, this is what skewness is about. Now, what kind of a values can A3 be negative? If we look at our definition of A3, so if let us say we take particular distribution which is skewed to the left. Okay. So, this is skewed to the right. Okay. So, this is going to be my mode, my mean will, this will be where my mean will lie, okay, and this will be where my median will lie. Okay. So, what you can clearly see is when I do this computation for A3, it tells me that there are many number of points which are less than my mean. So, this is my y bar value, and for all these values I am going to get this component will return me a negative value, okay, and only for few of the others this quantity is going to be return me a positive value. So, when I actually do this calculation, I am going to get a value of A3 which is going to be negative. So, A3 is going to be negative for this kind of distributions. Okay. So, we will do one sample calculation to see whether what we think will remain it like that. Okay. On the other case, so in the other case, if it is skewed in the other direction, if you have a distribution like this, so this is your mode, this is your here is where your mean will lie. So, I can clearly see that for all these points which are to the right of the mean, y minus y bar is going to be positive. Okay. And as by this token I will get a value of A3 which is positive. Okay. So, let us take a sample example. Let us take a sample example where we calculate the skewness of a distribution. Okay. So, let me write down some numbers which kind of portray this picture. So, let us say my variables are 1 1 1 sorry 1. Okay. So, this is doing this particular kind of a case. So, 1 1 1 1 2 3 4 okay 3 4 5 6 7 okay. Let us do this distribution. Okay. You have 3 ones 1 2 1 3 1 4. So, your y bar is equal to 3 plus 2 plus 3 plus 4 by 6 is equal to 6 10 12 is 2. Y bar is 2. Now, I can calculate my y minus y bar. So, I have 1 1 1 2 3 4. Okay. So, for value of 1 it is minus 1 minus 1 minus 1 0 1 2. Okay. So, in this case y minus y bar whole cubed will give me minus 1 minus 1 minus 1 0 1 2 cubed is 8. Okay. So, in this particular case, okay, even though the distribution is y to the left, I can see that summation y minus y bar whole cubed will give me a value of 3 plus 3 4 6, right. So, in this case it is, though it is skewed to the left, it is still A3 is giving me a value which is kind of positive. Okay. So, but you can see that if these numbers were much to the left, okay, so if you had few more of 2 3 4 and you had one number as 8 and you did the you had 2 more of 2 3 more of 2 and do this for this particular distribution, you might see that this will slowly become negative. Okay. So, with that I conclude today's class. So, what we have done is come up with this metric of skewness. So, starting from standard deviation and going to how we want to do relative standing by using z-score, and then from there we went on to see how you can come up with relative matrix of finding out moments and coming up with matrix to characterize the way a distribution is. Okay. So, skewness gives us the value for any symmetric distribution. Skewness will return you a value of 0, but typically if it is biased, if most of your data lies to the left of your mean, then sometimes this skewness value can be negative, versus if your data is to the right, it can be positive. Okay. With that I conclude today's lecture. Thank you for your attention.